So we continue with convolution. Remember, we defined the convolution of two functions related to the Fourier transform. When we say related to the Fourier transform, so what we mean is, just to remind you, we mean that if you take the convolution of two functions, this is the notation, and you find the Fourier transform of this new function, it will be root 2 pi the Fourier transform of the first function times the Fourier transform of the second function. And this was the target for the convolution, to have some operation, which is the convolution, whose Fourier transform is the product of the two transforms. However, we get the extra root 2 pi because of our definition for the convolution. Okay. We already did two examples. Remember, we had quickly this example, e to the minus absolute value of x with itself. This was our last example. Before that, we had another example, e to the minus absolute x with the rectangle function. What I mean by the rectangle function is the function 1 if x is between -1 and 1 and 0 otherwise. So in this example, I want to find the convolution of the function with itself. So this is our goal in this last example. So this will be the last example I solve on convolution. I think the idea then will be very, very clear. Okay, so what is this function? This is between -1 and 1, it's 1. And remember, these vertical lines that we draw are not part of the curve. We just draw them for, just to make it look nicer, that's it. So this is the function f. Now let's remember the geometric meaning. So before starting the computations, I like to remind you, because this the geometric point of view is very important for us to understand what's going on, especially for engineers. What do we mean by the convolution? You draw this function, that's it, and then you look at the other function, which is the same function in this example. We are finding the convolution of the function with itself. So the other function is the same thing. You reflect it about the y-axis, you get exactly the same thing. Then you shift it by x units to the left and to the right. If x is negative, to the left. If x is positive, to the right. So if we extend, just to remind you of this stuff, so if we extend the axis so that we have more space, and we draw the shifted function. So again, you reflect this blue curve about the y-axis, it's the same thing. Then you shift it by x units to the back, if x was negative, and to the right if x is negative. So basically, if this is -1 and this is 1, when you shift it, what happens is this becomes 1 plus x, this becomes -1 minus x. This is exactly what happens, -1 plus x, sorry. This is exactly what happens when you shift the function by x units. Just to make this clear, for example, imagine x was -2. So in that case, the -1 has to go to -3, which is -1 plus -2. And the 1, when you shift it 2 units back, it has to be -1, which is 1 plus -2. On the other hand, if you shift it right by 2 units, so if x was +2, for example, the 1 has to go to 3, which is 1 plus 2, and the -1 has to go to -1 plus 2. So this is the new rectangle. So it's always from -1 plus x to to 1 plus x. Okay. Now what happens is, this is the function, and you imagine this rectangle is walking to the right. Okay, it's running to the right this way. So you need to look at this rectangle with every x. You look at the new graph. So you change x, you look at the new graph. So for example, this is one scenario. This is one scenario for the graph where 1 plus x is smaller than -1. So this is one scenario. Another scenario that we could have is, so I'm going to draw the function again. So I'm drawing the different scenarios that you will see in our computations. The other scenario, again, this function is still the same thing, outside is 0. And for the red one, when you just imagine this red rectangle is running to the right. At a certain point, there will be some intersection between the red and the blue rectangles. So just imagine the red rectangle looks like this. So this is 1 plus x, this is minus 1 plus x. Again, outside these rectangles, everything is 0. The other scenario that we can have is, sorry, let's stick to the colors so everything becomes consistent. So this is again the original one. So the other scenario is what happens if when you shift your rectangle. Just imagine when you shift your rectangle becomes something like this. And for the other case, imagine what happens if this is your original rectangle, and when you shift the red one, you get something like this. Okay, so these are the different scenarios that we can have for these, like the relations, the different relations between the blue and the red curve. Now, what do we mean by the relation? Now, in the convolution formula, just to remind you, in the convolution formula, this is the definition. So if I write the definition here, it's the integral from negative infinity to infinity, one of the two functions times the other function, g of x minus t. And in my example, g is the same as f, so I'm having f of x minus t dt. So you are multiplying both functions. Now, if you look at the first case, what do we mean by you multiply the two functions? Now, the x-axis represents the t values. So you take every single t. So let's change. We need a new color, but I'm not using the green. It looks odd on the screen. So for example, if you take any value for t here to the right, if you take any value for t, and then you ask, what happens when you multiply the blue function with the red function? You get 0, because at those points to the right of 1, everything is 0. What happens if you take any t here? When you multiply again, okay, between negative 1 and 1, the blue function is 1, but the red function is 0. So when you multiply them, you get 0. And what happens here? You get 0. And what happens here? You get 0. So it is very clear. It is very clear that for the first case, when you compute the convolution for the first case, for those values of x that make the rectangles look this way, it is 0 exactly. The same thing if you look at the last case. If you look at the last case and you ask, what is the convolution for those values of x? You just apply the same idea. So you take all x values here, the t values, I mean, that give you this figure. So the x values that give you this figure. So you take any t here or there or there, and you multiply the red with the blue functions, you get 0. So for us, if the red curve is to the left of negative 1, what does it mean? What does it mean? That means, so in this case, we're talking about if 1 plus x is less than or equal to negative 1. The equality doesn't change anything because my functions are continuous. All the time, the convolution is continuous. So you don't need to worry about the equalities. So in this case, x is less than negative 2. So basically what you are saying is that when you compute the convolution, if x was less than negative 2, you will get 0. For the last one, what is this case? So again, this number here is negative 1 plus x. This number here is 1 plus x. So what do we mean by this figure here? We mean that negative 1 plus x is bigger than 1, right? Because this number here is 1. So basically, if x is bigger than 2. So for sure, when we compute the convolution, if x is less than negative 2 or equal to negative 2, you will get 0. And this is the first figure. For the last figure, if x is bigger than 2, the convolution will be 0. So what's left basically is to look at the other two cases and to ask what are these cases. So for this case, what we are talking about is that just when is minus 1 plus x, I want it to be less than negative 1. At the same time, I want 1 plus x to be less than 1. Okay, minus 1 plus x less than, this is the 1, this is the negative 1, and of course I want this value to be bigger than negative 1, okay, because I want the two rectangles to be intersecting this way. So this number 1 plus x, I want it to be between negative 1 and 1. This number negative 1 plus x, I want it to be less than negative 1. So if you solve for this, the x has to be less than 0. If you solve for this, the x has to be less than 0 and bigger than negative 2, right? So what you are saying is that when x is between negative 2 and 0, you will get something like this. You will get this is the case we're talking about. So you will get something like this. What do you mean by you get something like this? That means when you compute the convolution, now you are integrating over t from negative infinity to infinity. But in this case, again, if you look at those t values, there is nothing to multiply. You have zeros. The same for values here, right? The only values that you multiply and you don't get 0 are from negative 1, from, let me change the color again, I'm using the green. So this is the negative 1, this is the 1 plus x. Between them, if you take any value for t, then the two functions are 1. So when you multiply them, you get 1. But otherwise, if you take any value outside this green area, let's say, if it's outside like here or there, then you will get 0. That means when you integrate the function, you just take the integral from minus 1 plus x up to minus 1. That's it. For what? For the product of two functions, which is just 1 dt. And if you integrate the dt, it's t from the upper limit minus the lower limit. So you get minus 1 minus minus 1 plus x, which is minus x. So if x is between negative 2 and 0, then you will get the convolution equal to, sorry, I did this mistake, sorry. Okay, back please. So when x is between negative 2 and 0, and you look at this green area, the green area is from negative 1, sorry, it's not from negative 1 plus x, it's from negative 1 to 1 plus x for 1 dt, and if you subtract it, you will have 1 plus x minus minus 1, so it is 2 plus x. So this is telling you that when you compute the convolution and x is between negative 2 and 0, this is exactly what you're going to have. You're going to have 2 plus x. Then you look at the third figure, at this figure. What do you need here? This is again negative 1, this is 1, this is 1 plus x, this is negative 1 plus x, right? So for this case, what you're saying is 1 plus x, you want it to be bigger than 1, which means x is bigger than 0. At the same time, you want the negative 1 plus x to be bigger than negative 1 and less than 1. So to guarantee this kind of intersection, this number here, the negative 1 plus x, has to be in the middle of the blue rectangle, which is between negative 1 and 1. So this is what we should have, which means x is less than 2 and bigger than 0, right? So if x is between 0 and 2, this is what you're going to have. And in this case, the integral becomes, now if you look at this this figure here, if t was any value here, the product of the two functions is 0. Even if it was here, the product is still 0 because in this area, the red function is 1, but the blue function is 0. So when you multiply them, you get 0. The only region where the functions, the product of the two functions is not 0 is this green one. So what happens in this green one is the limits are, from negative 1 plus x up to 1. And when you multiply the two functions, they are both 1. So it's 1 dt, and this is 1 minus minus 1 plus x, which is 2 minus x. So this tells you that when x is between 0 and 2, this is the convolution. So basically this is the graphical way we compute or we look at the convolution. So my conclusion is that when you compute the convolution of this function with itself, what you're going to have is, let's go back. for the first case, it's 0 when x is less than -2. When x is between -2 and 0, you're getting x plus 2 when x is between -2 and 0. When x is between 0 and 2, you're getting 2 minus x, and you get 0 when x is bigger than 2. This is exactly our convolution. Again, the equalities, you can add them anywhere because the convolution is always continuous. So for example, the -2, if you like, you can add it here, you can add it in the other one, and you must have seen already that the two rules, the 0 and the x plus 2, give you exactly the same number when x is equal to -2, and this is the meaning of continuity. And by the way, this is one indication, as we mentioned in a previous video, this is one indication that you are doing things right. So after you compute your convolution, especially when the functions, the original functions, are not continuous, if you get a continuous function, that is an indication that you are doing fine. And by the way, when you watched the video, I'm sure you observed the mistake I did in the second figure. I did a mistake, and the reason why I doubted my solution, I questioned my solution, the reason was because when I obtained this value, it wasn't continuous at -2. Because I knew from the first case that at -2 we must get 0. But when I computed this in the first solution, I had -x, and the -x doesn't give me 0 when x is -2. This is why I doubted my solution, and I discovered that I did a mistake. So again, these are just indications if the function is continuous, after computing the convolution, if it's continuous, this is an indication that your solution is correct. So these are the equalities. I'm just going to add them this way. You can add them, by the way, everywhere because substituting them anywhere gives you the same value. So this is the graphical computation of the convolution. Now, some people prefer this graphical method. Some people like it. Like me, I'm a mathematician. I prefer the math. But engineers prefer this method for solving. I'm sure they have their reasons. Now, what about